The question that I have is, could you do a 1D consolidation example? This is the example that I want to do here. We have a clay layer of thickness 6 meters sandwiched between two sand layers. The water table is at a depth of 2 meters and the ground is subjected to a surface pressure of 50 kilopascal. So this problem has to do with the consolidation that will initiate from the time the surface pressure is applied. Of course, you can assume that the surface pressure is applied instantaneously. The properties of the clay layer are given, the relevant properties. We have a value for the coefficient of consolidation and we also have a value for the coefficient of volume change m sub b. These are the questions. We want to calculate the pour water pressure at point A 2 years after the application of the load. We want to calculate the ultimate settlement of the ground surface. We want to calculate the settlement of the ground surface 2 years after the application of the load. And also the settlement of the ground surface 2 years after the application of the load if the bedrock had been right at the bottom of the clay layer. The third part of this problem concerns this problem, which is a doubly drained problem. The fourth part concerns a what if situation. What if this problem had actually been a singly drained problem? Let's go ahead and do the first part of the problem. We want to calculate the pour water pressure at point A 2 years after the application of the load. The pour pressure at point A consists of two parts: the initial hydrostatic pressure, U naught, and the excess pour water pressure 2 years after, little u. The calculation of U naught is pretty straightforward. U naught equals gamma W multiplied by H, where gamma W is the unit weight of water, H is the depth of point A from the water table, which in this case is 2 plus 1.5, which is 3.5 meters. And of course the unit weight of water is 9.81 kilonewton per meter cubed. So that formula gives us a value of 34.34 kilopascal for U naught. To determine the excess pour water pressure 2 years after the application of the load, we're going to have to utilize this local degree of consolidation chart. The steps are that we calculate a value for the time factor T, we calculate a value for the dimensionless depth capital Z, and then we go to this chart and find a value for uz, right? The time factor is calculated to be 0.35. We have a value for C sub V, which is 5 times 10 to the minus 4 centimeters squared per second. And the time is 2 years. And since the coefficient of consolidation is given in centimeters per second, we want to convert this into seconds. So I multiply 2 by 365 and then 24 and then 60 and then 60 again. And so that'll give me the time in second. And this is a doubly drained problem. We have sand here, and therefore H to be used in this equation is 3 meters, half of the thickness of the clay layer. Once again, we want to convert that into centimeters so that this centimeter squared and this centimeter squared will cancel out. Remember, time factor is a dimensionless quantity, right? So everything should cancel out to give us no dimension for the time factor. So H is 300 centimeters, and you square that, and I get a value of 3.35 out of that. The dimensionless depth would be Z, which is 1.65 meters, divided by H, which is 3 meters. So we have a value for 0.5. Now for this combination, T equals 0.35 and Z equals 0.5, we want to find a value for the local degree of consolidation, UZ. So I draw a horizontal line at a dimensionless depth of 0.5. And I go to the time factor curve that corresponds to 0.35. So you can see we don't have a curve. We do have a curve for 0.3 and we have another one for 0.4. So it's going to be in between the two. So this is an approximate interpolation, and we get a value of 0.61 from this. But if you want to be a little bit more precise, you can calculate this value, the value corresponding to a time factor of 0.3, and a value corresponding to a time factor of 0.4, and then interpolate in between. Now we use the definition of the local degree of consolidation to calculate the excess per water pressure. Local degree of consolidation is defined as U naught minus U over U naught, where U naught is the initial excess per water pressure. So in this particular case, since the increase in the total stress throughout the clay layer is uniform and equal to 50 kilopascal, the initial excess per water pressure within the clay layer will be constant from top to bottom and equals to 50 kilopascal, right? So that gives us a value of 19.5 kilopascal for the excess per water pressure. Now to answer the question, we add the two, the initial per water pressure, which is 34.34 kilopascal, the excess per water pressure, which is 19.5 kilopascal, and we get a total per water pressure at point A 2 years after the application of the load of 53.84 kilopascal. Now let's do the second part of the question, which is to find the ultimate settlement of the ground surface. We need to work with the properties that are given to us. What is given to us here is m sub v, the coefficient of volume change, right? So the formula to be used here for calculating the ultimate settlement is this: S infinity equals mv multiplied by delta sigma v multiplied by h, where mv is the coefficient of volume change, delta sigma v is the change in the vertical stress, and h is the total thickness of the clay layer. The change in the vertical stress comes from the surface pressure of 50 kilopascal. The total thickness of the clay layer is 6 meters, and you substitute these numbers and I get a value of 0.3 meters for S infinity. Once again, let me emphasize that h that goes in this formula is the total thickness, and calculation of the ultimate settlement has nothing to do with the drainage conditions for the clay layer. So every part of the clay is going to make a contribution to S infinity, and therefore we use the total thickness here. Now on to the third part of the problem, which is to calculate the settlement of the ground surface 2 years after the application of the load. To complete this part, we need to use this relationship between U average and T, where U average is the average degree of consolidation. If you recall, we have shown that U average equals S over S infinity. So S over S infinity equals U average, and therefore we can calculate S from that equation. We've already calculated the time factor in the earlier slide. Remember, time factor is 0.35, right? So we go to this chart, and for 0.35, we draw a vertical line, and that line is going to cut the curve at this point, and we come horizontally to this vertical axis, and we get a value of 65% for U average. And therefore S, the settlement of the ground surface 2 years after the application of the load, is 0.65 multiplied by 0.3, which is 0.195 meters. The last part of the question concerns one of those what-if situations. What if the bedrock had been right here at the base of the clay layer? It's implied in this question that everything else remains the same. So all we have to do is to recalculate the time factor. Why? Because now the problem is a singly drained problem. And therefore the value of h to be used in the time factor equation, which is this, is 6 meters, not 3 meters anymore. Alright? So the whole thing, the entire thickness of the clay layer becomes equal to h. So using 6 meters in this expression, we get a value of 0.0875 for the time factor. Now we go back to this chart, U average versus T chart, and for 0.0875 of time factor, we get a value of roughly 32% for U average. So using 32%, we recalculate the settlement 2 years after the application of the load, and that works out to be 0.096 meters. So what is happening here is that because the problem is singly drained now, the rate of settlement is slower. When the problem was doubly drained, U average was 65%. Now it's basically cut down to about half of that, 32%.